So yesterday we discussed about order statistics, the selection problem. Given n elements, find k as the smallest element. And what we found that for this task, we actually have a worst case ON algorithm. Okay. That was something we did not know before talking about order statistics, that we can actually have an order and worst case algorithm for this. Anybody has a difficulty understanding this algorithm, first of all? You're not able to understand this algorithm or anything that we discussed yesterday? Okay. So again, this is the bigger picture. Find pivot, partition using pivot, okay, and then a recursive algorithm that will go into one of the subarrays. And what is crucial here is finding pivot. Finding pivot, you first break into groups of 5, find median of each group by a simple method. Yes, use n by 5 medians, and then recursively call the selection algorithm on this array of medians, get the median of this array. Okay. And that becomes a pivot. That's all. And we discussed the complexity. This will be Tn by 5 plus T7n by 10 plus On. If you think about it, it is as if you are throwing n by 10 elements every time. So some fraction of elements are removed every time. So you're only working with 7n by 10 plus n by 5, 9n by 10 elements. Okay. Yes.
Sir, in the calculation part, sir, can we add these to T?
What do you mean?
Sir, I mean writing Tn by 5 plus T7n by 10 as T9n by 10.
No. That we cannot do in general. I'm doing it here because just to show that, okay, it is as if you are using 9n by 10 elements. And finally, this comes out to be an order n algorithm. That's where you can actually add. It's Tn is On. So that is the reason you can actually talk about adding this. But in general, not.
Okay, sir.
Because suppose, and this is a function of n as n square, you cannot add these. Right? You cannot say T of n plus T of n. Yeah. Maybe they will be of the same order, but yeah, this will not be exact to just add. You cannot do that. Just a function of n. But it's a linear function, so yes, you can. Linear function, you can. So you're throwing away n by 10 elements every time. And towards that, I also said that using this algorithm, you can also make quick sort h worst case n log n. So how to use that to make quick sort O(n) log n in the worst case? What will you do?
We will find the
We
median.
will find the pivot by this method.
Oh, just find the median. Yeah, just find the median. So find median of the array as selection A and n by 2 and use this as pivot. That's all. So I have something additional order and time for finding the pivot. Everything else remains the same. And this pivot means that arrays are broken equally. n by 2, n by 2 each using the partition. So they will be broken equally. So then the complexity is O(n) log n. Simple. Now the next question that you had, okay, so fine, what we do here, we take this array of size n, break into groups of 5 each. Find medians and their median. Okay, and we use that. What is something special about 5? What is something special about 5? Why can't we do with 3? Or why not 7? Okay, that was a question yesterday. Let's try with 3. Let's try with 3. Okay, so what I will do,
So with 3, the sum will be greater than n, I think.
okay, let's check. So I'll break into groups of 3 each. Okay, and I find n by 3 medians. Now I call selection algorithm for finding out the median of this of n by 3 medians. And this is suppose x. Now what can we say about how many elements are guaranteed to be smaller than x? So we know that n by 6 here. N by 6 plus for each of these n by 6 medians.
N by 6.
So for each of these n by 6 medians.
N by 3.
Each of these medians, I go. So one more element will be smaller than x, right? So again n by 6 or 2 times n by 6. So that is n by 3. So that means you're guaranteed to have at least n by 3 elements that are smaller than x and at least n by 3 elements that are larger than x. Okay, fine. So if I have this, so what will be my formulation of Tn? So Tn, I have an order n term that remains there, plus I am recursively calling the algorithm for n by 3 medians. So I'll have a term T of n by 3. And I have to take into account the worst case. What is the largest number of elements in one of the sub-arrays I can have? What will be that?
2.
2n by 3? Because I'm only guaranteed to have n by 3 elements in each, right? So in the worst case, the sub-array I go to may have 2n by 3 elements. So this will be the formulation. And yeah, as one of you said that, yeah, these together, you see they are n. That means you have to use all the elements again. Okay, and this will actually give you order n log n. Right? Because we have seen that in the case of quicksort also. If you partition them into n by 3 to n by 3 and apply, you get order n log n. So this gives you order n log n. So 3 replacing 5 by 3 does not help you at all. This gives you order n log n. Not good. Okay. Why not 3 will not work. Why not 7? What will happen if we take 7? Okay. Let's take 7. So I have n by 7 groups. I find median, so n by 7 medians. Okay, then again I find the median of this, of these, call it x. Now, how many elements are smaller than x? guaranteed to be is smaller than x. So in the n by 7 medians, x is the median of this. So n by 14 elements are guaranteed to be smaller. So n by 14 medians. Now let's take one of this median. Here I have the median y. So 3 elements are smaller, 3 elements are larger. Okay, so that means guaranteed to be there will be another multiply by a factor of 4. 1 plus 3, 4. So that means for each median, another 3 elements are smaller than x. So 2n by 7. At least 2n by 7 elements are smaller than x. Okay. So then what will be the formulation? Tn in the worst case, there is an O(n) term, fine. What is the recursive call? This recursive call is going to n by 7 medians. Yes. Plus in the worst case, what is the longest subarray I will have to go to?
5n by 7.
5n by 7. Because each array will have at least 2n by 7, the longest may have 5n by 7. Okay. And these two are still less than n. This is 6n by 7. So if you solve this, you get TNH ON again. Okay. And you see how many elements you are throwing away. So here you are throwing away n by 7 elements each time. And n is equal to 5. How many you were throwing? Oh, sorry, not n is equal to 5. With groups of size 5. These groups of size 7. How many you were throwing away?
n by 10.
N by 10. Each time. Oh, so that looks like okay. With 7, you will throw more elements each time. You will throw more elements each time.
Sir, I didn't get this throw part, sir.
Throw. Okay, so this is just the notation we were using. So we were saying, okay, overall you have n elements, right? And you recursively call the algorithm on some subpart. Like here, you're calling once on n by 7, once on 5n by 7. So if you see like that, you are using 6n by 7 elements, calling them, but n by 7 elements you're not using at all. So you're throwing n by 7 elements each time. That's what I mean.
Okay, sir, got it.
And similarly, in the previous formulation, we saw there were n by 10 elements we were throwing. 2n by 10, 7n by 10. So n by 10 elements we were throwing. So it looks like with 7 you will throw more elements. So why not 7? Why not 7?
Sir, for finding the median of each group, it will be large.
Yeah, so somewhere something should be something should be there. Otherwise, I can do 7, I can do 9, I can do 9, I can do 11, I can do 13. I can keep on doing increasing that, and I think this number will keep on reducing. I mean, increasing how many you are throwing. Okay, so yeah. So what will be the number for 9? Can we quickly find out? There will be n by 9 medians. So n by 18 times 5. Yes, 5n by 18. 5n by 18 and recursive call to n by 9. 7n by 18.
11n by 18 will be 3.
Oh yeah, sorry. So n by 9 and 2n by 18. Okay. So minimum this much. So the other array will have 13n by 18. Worst. Okay. plus 2n by 18, 5n by 18. So
N
you
by
will
6.
actually
N by 6.
n by 6. You will throw n by 6. So even more. You will throw even more. Okay. So that means if you can do with 5, you can do with 7, 9, 11, any number afterwards. You can do this. Okay. And the number of elements you throw is more. And so that means it is good, right? But now you think, why can't, so if I can go from 5 to 7, I can go from 7 to 9, from 9 to 11, 11 to 13. Now what happens? Why don't I go? Why don't I go 9 to 11, 11 to 13? What is the issue?
The complexity is will increase. Time taken will increase.
Which complexity? What part?
So the
First
constant in order n will increase.
Yes.
The
So what will
constant
happen as you go from 5 to 7? What changes? Okay. So what changes is that you have to make groups. So one time you are making groups of 5 each. Another time you are making groups of 7 each. Okay. And what you're doing, you're finding median. You are finding median of each group. And that we said is your order n. But actually, what is the time you are taking? So let's say we use a simple algorithm that will be, so for group having size k, that will take k square time. You may use simply selection sort or whatever, some simple algorithm, because the number of elements are very, very small. So you will not go for an n log n type of complex algorithm. You will go for a simple algorithm. So then if I use k square time for each group, what is the time I take for groups of size 5? What is the total time?
25.
25.
5.
25. And how many groups?
N by 5.
And 5.
10 by 5.
5.
So this gives you 5. And if you have groups of size 7, then 7 square 49.
7n.
10 by 7, 7. Okay. So there's an increase in this ON thing. So it goes from 5n to 7n. Okay. So what happens is that the gain you are getting by throwing away some more elements is not as much as the loss you are having because of this. So this is a loss, and this loss is much more than the gain, than the small gain, because you are not gaining anything asymptotically. Okay, so because complexity is always order n, but what is happening? The constant is increasing that for order n. So that is why you can only do from starting from 5. You cannot do before 5. 3 is not possible. You can do with 5, 7, 9, 11, whatever. But among this, it is best to do with the smallest possible group, and that is 5. 5 is the smallest possible group with which you can do this. Because finding median of each group is not so easy. I mean, not so easy means not so efficient. Finding median for each group is not so efficient. That is the reason we only take 5. Okay, does that answer? Yes.
If you use k-log k algorithm for
No, you can
each
use
group,
that.
then you
That's
can.
also fine. Then also you will have the same problem. Then what will happen? You will have n. So suppose you are saying instead of k square. So first of all, for 5 elements, using an n log n algorithm does not give you much than the n square. But let's say, suppose we using.
It is possible taking 5 and order n square can be, can take more time than taking n equal to 7. Groups of 7 and sorting with this k log k. Is it possible?
Right, but then you can also use k log k in 5. Why not? Let's say we use k log k everywhere. Right? Let's say we use k log k everywhere for k is equal to 5 and k is equal to 7. So then you have k log k for each group, and there are n by k groups. So this gives you n log k. So that is n log 5. And here you get n log 7.
It will vary
But
logarithmic.
that increase is not much.
Huh?
N log 5 and N log 7, that increase is not much as in.
So how do you know that other part is giving you more? So this, okay, so other part is also not giving you much. Okay, so you are going from log 5 to log 7 and multiplying by that constant, right? So you're multiplying that constant. Order n is equal to some Cn, right? So you are going n times log 7 by 5. That much you are increasing here, your time complexity. And of course, we can do analysis of how much gain you get in the other part, how much gain you get in the other part. That one can possibly do. But yeah. Finally, that's what turns out. If you keep on doing 7, 9, 11, whatever I mean. So you see again there, you see a loss here. And yeah, they either balance out or sometimes this is even larger. The loss that you're having is even larger. Of course, if this term was not there, then this would not have made any sense. Then you could have taken any large group, right? But overall, you think, so what is happening? You are taking groups of a small size, finding medians of each group, and you would like to work with the smallest possible group. Okay. You would like to work with the smallest possible group, and that is where the smallest possible group with which it can work is 5. If you go below that, it cannot work. The 3 we have seen, it will not work. And after 5 it will work, but the smallest possible is 5. So that is the main idea.
Sir, also if we take large groups, then means coding it will be difficult, because then we have to write more and more number of base cases in the recursion.
Yeah. So that is true.
Sir,
Mm-hmm.
sir, is there a way of finding the median without sorting the array?
Yeah, here you're not sorting the array and finding median, right? The algorithm we're talking about, we are doing it without sorting. We have not sorted, isn't it?
Sir, the smaller array, I mean the array of 5 elements, that group.
Oh yes, you can find the median, but how will you do that? How will you find the median without sorting? You have to find the, say, 5 elements, the first largest, second largest, third largest. Third largest element.
So, sir, if else ladder is required, right? Comparison.
Yes.
So if we sort, we get 25 comparisons, and if we do by this, we get 15. But will that matter?
That will not matter. 15, see, it will again multiply by that, right? If you have 7, you will get then 15, whatever. If you take 7, it will increase, right? It will increase with 7.
Yes.
Then you go 5 to 7. So the amount by which this increases is there. So that is where the issue is. The time in which you can find median of 5 and time in which you can find median of 7 are not the same. You will take more time in finding median for 7 elements. And that is what kills. So that is why you cannot go for larger groups. So actually, if you can even see, what is the minimum number of comparisons to find the second largest element. If there are n elements overall. What is the minimum number of comparisons we will need?
3n by 2 minus 1.
3n by 2 minus 1. How? Second largest.
So dividing the array into 2 halves and recursively doing. And base cases were if there are 2 elements, there is one comparison, and if it is one element, we will return.
So you are saying, okay, I can divide into 2 parts. Okay. N by 2 each. Then in each part, you find the maximum in each part. N by 2 minus 1, n by 2 minus 1. Okay. Then so this gives you n minus 2 comparisons. You know the maximum here and maximum here. Now what is the next thing you will do? Second max can be anywhere. So first of all, I think you have to find out the max among these two.
So I thought like I can do how we do for finding minimum and max.
That's what I'm asking. How exactly? Yeah, I think what I can think of right now from here, you do one more comparison between this, compare this one, and suppose one of this, suppose this is the max. So you know the second max is either here. So second max is either in the left part or the max 2 or max 2. One of this is the second max. Yes. So you will compare max 2 with the left part. Compare max 2 with n by 2 minus 1 elements of the left part. So that means you need another n by 2 minus 1 comparisons, and this will give you an answer, right? Finally. So n minus 1 plus n by 2 minus 1. 3n by 2 minus 2 is what I think. Unless I made a mistake.
Sir, sir, can we apply the same algorithm for the smaller groups?
Yes, yes, yes. We can do it recursively. We can do it recursively. So it turns out, yeah. So this is a simple way of thinking. You can do 3n by 2 minus 2. But yeah, why can't I keep on doing this recursively? Okay. So now, what is the minimum number of comparisons? To find second largest element. So again, think in terms of tournament once. Think again in terms of tournament. So we saw that you need n minus 1 games to find the winner. Minimum. Let's say exactly if you are doing knockout, you need n minus 1 games to find the winner. Yes. Now, how do you find the second best? Yes. Who will be the second best?
The last game runner.
Hmm?
The last game runner.
The last
Games runner.
game's runner. What do you mean?
Like the last match happens between.
Whoever played the final, like who lost the final.
Sir, like we can do whoever lost to the best. We can means the tournament winner among the ones who lost to the best.
Yeah. Yeah. See, when you are saying he would have lost as the final, you are assuming many things. That there would be a particular structure and there would be a final. But you see, think about your elements again. So the second largest element might be knocked out first time itself, in the first game itself with the best. If he plays with the best in the first game, he would be knocked out immediately, right? So he might not be able to play other games to show that he is the second best. Yes. So suppose your array has 10 elements and the largest and second largest are in the beginning. So the second largest will lose immediately, right? So last game runner assumes something, but in general, what you can say, would have lost to the winner, for sure. Because the second best, nobody else can defeat that second best team. The winner has to defeat in some game. Would have lost to the winner in one of the games. Or in the game that happened between them. There has to be a game that's where the second best got defeated with the winner. Right? Otherwise, how will it go out? Second best. But it can go out anytime. Whenever it plays a game with the winner, it will go out. So then what does that mean? So how do you find out the second best? So for that, you have to see all teams who have lost to the winner. Okay, let's suppose you find there are k teams. So then you know that you have to find the best among this. So this will take k minus 1. So if there are k teams, so you need k minus 1 comparisons. Or find the best among the k, you will need k minus 1 comparisons. So total n minus 1 plus k minus 1. So what is the minimum number of comparisons? So the way we do, like in our simple algorithm, what we do, we play each one we play with the winner. So the winner actually plays with each one, right? One of them loses and another again plays. Right. So the winner keeps on playing with all the teams, all the n minus 1 comparisons. So there are actually n minus 1 losers. N minus 1 losers. So that means you will need n minus 1 plus n minus 2. 3n minus 3. Oh, sorry, 2n minus 3. But we already saw we have better than this. So now, question is, how can we minimize k?
How did we say that this is the minimum amount of k, like n minus 1?
No, I didn't say that. I said the naive algorithm we do. We take k as we take k as.
Sir, we can do like that. Player number 1 plays with 2, player number 3 plays with 4. Then the winner of these two play with
You
each
have to
other.
minimize k. You have to minimize k. So minimize the matches that the winner plays. Still, so what you will do, you will follow the strategy that okay, I have suppose n is 2 to the power some L. So just to make the visualization simple, you group them. And one of them is winner, again you group them. Okay, somebody forgot to mute. Okay. Keep on playing, right? Again, you find the winners. So you see, you actually get a tree structure. Finally, you have 2 games and 1 winner. So in this case, how many games did the winner play?
So login.
Login games. Okay, and you can maybe say something like login. That many games the winner played, and that means that many people lost. Okay, so you have to make comparisons between this. So again, you need n-1 plus log n minus 1. So this is the minimum number of comparisons to find the second largest.
But sir, this is when we know that we have sorted them in increasing order, then only it will be log based.
No, we have not sorted them in any order. You have not sorted anywhere. Where have you sorted? You take any order and do this grouping, and this will be fine. I'm
Yes,
not sorting them anywhere.
Understood.
Sorting, if you use them, there is nothing. If you sorting them, you just take the first and second index.
So, sir, what have you done? Can you explain again?
No, see what we said. I want to find the second best person. So
Yes.
second best person can only lose to the winner, cannot lose to anyone else, right? So that means I have to find out all the people or all the teams that have lost to the winner and find the best among them by again doing matches. Okay, so that is where we said fine. So suppose there are k teams that have lost, so I need another k-1 comparisons. So total n-1 plus k-1. And I said, okay, one naive way that like we do in our find max algorithm is, oh, you keep on comparing max with each element, and one loses, and that's how it goes. Okay, so there will be n-1 people who will lose in our naive way. Okay, so that means I need these many comparisons. But the question is, to minimize the number of comparisons, I have to minimize k.
Sir,
Yes.
sir, while minimizing the k, we are means increasing the number of comparisons between means the other elements, sir. Like excluding the max 1 and max 2, we are also increasing the comparison between other elements, sir. Like there would be many comparisons here, sir.
No. See, remember again last time somebody said it's a knockout. How can they win?
Yes, sir. N by 2 plus N by 4. Yes, sir.
Yes, there cannot be more than n-1 matches. Every time one team knocks out. So there are exactly n-1 matches. Okay, in this way also. And then again, you're saying log n people are losing to the winner. So you do a comparison between them. So that will be plus log n minus 1. That's all. Okay, any confusion here?
Sir, can't we find the first winner also like this?
Find less than n-1. Find. Tell me how.
Like, sir, this only we will compare the adjacent ones.
How many comparisons you need?
So n by 2.
All these comparisons to find the winner. So that is n-1.
Yes.
Yeah, can't do better than n-1.
Yes.
Everyone, one has to lose. They have to be given a chance to show that they are the best, right? You can't just say, oh no, we cannot be the best. Some n-2 elements. No, they have to be given a chance to fight the winner. Okay. Good. So now, yeah, it's time. Okay, I'll just ask one more question. I think that's it.
Sir,
So,
Sir, this number you got n minus 1 plus log base to n minus 1. Sir, how do we like know that this is the minimum of all possible algorithms?
Yeah, that's a good question. How do we know this is the minimum of all, right? But you see what we have done, we have gone from that very logic that, okay, I need to find the best, then I need to find the second best. And second best has to be lost from the winner. Right? Otherwise, how will you find that? And there we try to minimize what is the minimum value of k you can get. That is where we have come to this. Like even in n minus 1, right? How do you show that there is no other algorithm that can give you the best in less than n minus 1 times?
Sir, there we had an argument that each match can eliminate exactly one team. So after the algorithm, there should be n minus 1 teams eliminated. So the minimum should be n minus 1. But how do we make sure? How do we get some similar kind of logic in this case?
See, that's a good thing. That's a good question. That's a good question. So what you are saying, oh, maybe there is another way by which I can find the second best in less than this. How do we show this is the minimum?
Yes, sir.
Yeah, I don't have a good answer for that. I don't have a good answer for that. How can you show that you cannot do it in less than this?
Sir? Sir, is this algorithm better than the median finding algorithm that we discussed before? Like just for finding the second largest, if we do that in that algorithm also.
No, you see, that algorithm gives you an asymptotic thing. Okay, so here you are getting order n. You are again getting order n. And minus 1 plus log n minus 1 is order n. So that algorithm already gives you an asymptotic bound that, okay, you can do it in order n time, any k. That's all. But here we are trying to find the exact number of comparisons. Okay. And how to show that this is the minimum for second best? I don't have a very good argument. Right?
Sir, can we tell that the minimum number of means we have to first find the first maximum always to find the second maximum?
Yeah, that's what I was doing.
Yes, sir. So minimum means for first maximum, the number of comparisons is one. And for the second maximum, the minimum number of comparison to reach till n minus 1 is log 2 base n minus 1. And that is the minimum number, sir.
No, that's exactly what we have done here. But
yes, sir.
But why can't there be another way by which you can find the second max? Why can't you directly find the second best without finding the best?
So that is not possible only. We cannot find second best until we know the best one.
If you take analogy from two people, then also it is impossible to find second best without finding the best.
Yeah, yeah. So what you're saying is that the way we can prove it is that, okay, I find second best, I have to first find first best, n minus 1. Then the second best. I mean, this goes to the same argument that we have done. It doesn't give any extra argument. Right? You are saying that is the proof in itself. Maybe. But I'm not very sure. Maybe there's a better way to prove it. But I'm saying we have gone through a reasoning by which we are saying this. But maybe there is a better way to prove it. So yeah, I'll look into that if there's a better way to prove that. But okay, yeah, from the reasoning we have shown that this is the best. But is there some way to prove it more formally? I don't know. Sure. I'll see if I can find something more formal. Okay, so sure. What else? So we have come to the end of this course then. So theory, all the labs classes with yesterday's lab are over, and today is the last theory class, so that is also over. And you will have one more class test, and hopefully you will be happy that this course is over. Okay. Sure. So anything else before we end?
Thank you, sir.
So few more problems.
So you want some more problems on this topic?
Yes, sir. Not only on this, means all the topics combined, which are the fourth test.
Okay, I can send some problems. But yeah, you see algorithms, you find problems everywhere. Okay, I'll send some more problems on at least this topic and see if some more problems I can send for the previous topics. Okay, what else? So fine, I think then you've gone through the course. So please, now you have to practice on your own. And I think you all know what is the importance of algorithms for throughout your stay and beyond. So you should, I think you have got the topics, but yeah, that's not all. You have to practice on your own, and that's how you will get more efficient with this. Okay, and yeah, thanks for being in the class so that we could teach. Yes, your being in the class is very important, and thanks for doing some very nice discussions. So every time we teach, we learn a lot. So this time also, I think I have learned a lot from all of you. So okay, so with that, I think I'll close the classes formally, and yeah, we will anyway remain in touch, at least this semester, and of course later on. And hopefully I'll see you sometime in the campus soon. Okay, so thanks.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you for everything.
Thank you, sir.